Today we have a special guest. So usually we have researchers from either Paris or Beijing presenting each other, but sometimes we also have external invitations. So today we have a special guest from Delft University. So I'm very happy to have today Dr. Michiel DE BOK. So he's a researcher at Technical University of Delft. And also research leader at Significance. He's responsible for mass GT freight micro simulation, and he's also involved in the Harmony project. He has a PhD and master degree in civil engineering in the field of transport planning. So Michiel is in the department of transport and planning at TU Delft, and so he has a lot of publication in the area of agent-based simulation, and especially in relation to goods transport and the logistics. So I'm very happy to have you here, Michiel, and very happy to hear about mass GT today. So the floor is yours.
Okay, Jacob, thank you very much for your introduction, and I'm happy for this invitation and to share our research with you. Of course, we are collaborating already in the lead project with you on these topics. Behind me virtually is the Delft University of Technology, the Faculty of Civil Engineering, where I work in part-time as a researcher. And indeed on the topic of city logistics and developing agent-based simulators for this. And I work closely with Professor Lori Tafassi at the department. And I'm happy today to present the mass GT model that we are developing at TU Delft and show you some of the applications that we are doing with it. Now, yes. I hope you see the next slide now in my presentation, so all the controls are working. What I will present in this seminar is, first of all, some background of why we are developing this model. Then I will discuss some technical details about the mass GT model and also the Harmony Tactical Freight Simulator. I will explain what I mean by that, and discuss two case studies that we have done with the model, one into zero emission city logistics, and another one in exploring decarbonisation scenarios for the road freight sector. Well, first of all, I realized that the Anthropolis, it covers more than just the city logistic domain, so also transport and passenger mobility. So first of all, I would like to elaborate shortly why city logistics is so important. This figure shows a statistical estimate of the vehicle kilometers in the city center of Rotterdam. And of course, passenger vehicles are by far the vehicles that make most vehicle kilometers. Heavy goods vehicles make up only 1.5% of the vehicle mileage. But in terms of emissions, it's a much more significant share. It's 18% currently. And of course, within the domain or within the segment of car vehicles, there are also a lot of vans and light commercial vehicles that are dealing with city logistics. So it's eminent that this is a very important segment in city logistics, or in urban transport, I should say. And it's also becoming increasingly important because the growth in urban freight transport is likely to be much larger than the growth in passenger mobility due to developments in e-commerce, for instance. So this is first of all about the importance of city logistics. Then secondly, what are the challenges in city logistics? And let me explain this by the story of Jos. Jos is a real person. He is our partner in the project Harmony. He's a city planner for the city of Rotterdam. So he is responsible to make sustainable plans to meet the policy objectives of the city. So this means that he has to keep the city accessible and reduce CO2 emissions and meet all the different policy objectives. And his field is quite complex because in the field of logistics, there are many big developments taking place. For instance, e-commerce, which I already referred to, but there's also plans for road user charges for freight vehicles. There's of course also the globalization of trade patterns. There's the Internet of Things, allowing more asset sharing, or changing also the way we optimize the logistical planning. And of course, zero emission vehicles, triple tuning, emission zones. So it's quite complex to make a good assessment in advance of what would be the impacts of all these investments, because space is scarce in the urban environment, resources are more and more scarce. So investments need to be made in a clever way, and so it would be great if you also would have decision support tool for this. Well, such decision support tools, they do exist, but over the past decades, there have been a number of different generations of strategic freight models, and this is just a way of presenting those. So for very many decades, there are aggregate freight demand models, like the Boswood model and the level with Transuls. More and more they have become more disaggregate. There are some examples here on the slide which are used more often in practice for freight transport planning. But more and more in the last years, there's more emphasis on microscopic simulators, agent-based models. Many of these models are being developed in the academic context and sometimes also commercially applied. So what we are aiming at in our project at TU Delft with MassGT, we want to contribute to this development and develop a microscopic simulator that is agent-based and at firm level, to have a better representation of the logistic behavior. Because many of the aggregate and the disaggregate models, they fall short in adequately describing logistic decision-making. Now, this also brings us to the objective of MassGT. The MassGT project, we want to develop a behavioral multi-agent microsimulation framework for strategic freight transport demand. The main assumptions in our way of working are a shipment and behavioral based model. So it is shipment based because much of the logistic decision making, it takes place around shipments. Many of the existing models, they simulate vehicles, but this is not the level at which decision making takes place, because within the vehicles there's a load, and this can consist of one individual shipment or a combination of shipments. So much of the logistic decision making about consolidation, it takes place at the level of shipments. Also, we want to develop a model evidence-based, so not just a theoretical model or with fictive numerical explorations, but based on large data. I will also tell more about that. And in order to manage complexity, we are developing the model in a stepwise incremental development process. One of the main projects that we are working on now is called the Harmony project. This is a Horizon 2020 project, so a European innovation program in which we are developing a number of simulators. And the role of TU Delft in this project is to develop a tactical freight simulator. And we are using MassGT as the model for this. Now let's go to the model. First of all, the conceptual model behind this. So we have agents, we have producers and consumers of goods, and the goods have to be transported between them. But many of these transports, they go directly, but in logistics, of course, a big share of transport are also indirect. So logistical nodes are used at distribution centers or multimodal transshipment terminals to have a more efficient transportation. And along this conceptual model, you can identify a number of logistical decisions that are being taken, like the choice for shipment size, the choice of vehicle type, or the desired delivery time. And the challenge is to capture all of these logistical decisions into your simulator. Well, we have developed a model for the Netherlands, for the province of South Holland. This is in the western part of the Netherlands. You see it here in the middle of this figure. It has a population of 3.5 million and it measures 3,000 square kilometers. Two of the major cities in the Netherlands fall within this province, namely the city of Rotterdam, with a very large seaport, and also the city of The Hague. Well, then the key design principles behind the MAS-CT model. Well, as I said, it's evidence-based and agent-based and shipment-based, so I don't need to repeat those. But we also implement a modular and modular structure. So we distinguish three different timescales. So first of all, there's a module called the Shipment and Parcel Demand module, and it simulates the longer-term strategic decision-making. So who do I choose as a producer or a supplier? What type of shipment size and vehicle type do I use for my transportation? These are decisions which are taken not on a daily basis, but more on a monthly or yearly basis, so to say. The second module is the scheduling module, and it simulates the daily decisions that are made in the logistical context. So it's the formation of round tours, so which of the deliveries or collection of shipments which can be consolidated in a round tour of multiple shipments. And of course also the delivery times that are required for this. And then finally there is the network module, and this is a rather simple static approach to just defining the shortest path of all the vehicles on a congested network. And this we use to identify the expected transportation cost along these routes, and also to calculate the emissions of all the vehicles. So this is roughly the outline of the model. I can also illustrate it by 6 figures to give you more feeling with the dimensions of the model. So there's a synthetic firm population. From this population, we can derive the demand for commodities and transportation. Then we calculate individual shipments, so the demand that is being sent around within and also outside and into the study area. On this figure on the top right-hand side, you see all the shipments between the distribution centers in the study area. And then finally, next, we also simulate the formation of round tours. So how are all the shipments that are being distributed from one of the distribution centers, how are they combinedly distributed within the study area? This is visualized in this plot. And then there's also a assignment, a simple or nothing assignment of the congested network of each of the individual vehicles, and from this we can derive emissions. Well, this is a lot of simulations, so it produces a lot of data, and from this we can derive aggregate key performance indicators. For instance, looking at which of the logistic segments are responsible for most of the CO2 emissions. And in this case, I've plotted it. You can see the general cargo and the transport of temperature controlled goods. They are both responsible almost for 1/3 of the CO2 emissions in the study area. Well, this figure shows the technical architecture. It's modular based. You can see the 3 layers. There's also 2 parallel structures in the model. So on the left-hand side, there's the shipment module, and next the scheduling module for all of these commodity flows. And this is the conventional freight transport. We also acknowledge that it's very important to also have partial demand separately in our model. And because this is a slightly different type of urban freight demand, we have developed in parallel a similar type of modular setup for partial demand. So first the module that calculates partial demand, given the locations of households and the location of the depots for the distribution of parcels, and also parcel scheduling. This all together gives you the tours and trips that you can use to feed a simulator. What we do now is to add the tours to our network module, but they can also be applied into other simulators. For instance, into the MATSIM simulators, which also in the case study that we're doing jointly between TU Delft in the lead project. We are also using tools to input into the MATSI simulator. So we are using the network module and indicator modules as auxiliary modules for to derive the necessary KPIs. And the population of freight agents, because in urban freight transportation, the logistic agents, they are very important. So we identified different types of logistic agents for this, so the logistic nodes. We have transshipment terminals and distribution centers. And since these are very important generators of freight traffic, we are not simulating them synthetically, but we are using real data for this. So there are databases available from which we can identify the locations of distribution centers and the parcel depots for carriers. And of course, also for the case of Rotterdam, the locations of the multimodal port terminals. You see them in purple on this map. And as you can see, the port of Rotterdam, it's a very extensive port. In addition to the logistic agents, we also have the final consumers and the producers of the goods. And these are represented by a synthetic firm population. They are plotted on this map on the left-hand side and a zoom in on the right-hand side. And then you can see that we have differentiated different size classes for the firms and also different types of industries. Then well, in this seminar, I cannot discuss the simulation models in detail, but to give you some idea about the modeling, it is necessary to show a bit the structure of the different modules. The shipment module is the module that simulates all the shipments that are being delivered and collected in the study area. For this, we have developed a top-down simulation approach. So in the stepwise procedure, the aggregate commodity demand is broken down into individual shipments and allocated to producers and consumers of the goods. And also the size of the shipment and the vehicle type is being simulated. The result of the simulator is then a set of all the synthetic shipments in the study area. The empirical basis for this model is an extensive transport data set that we derived from Statistics Netherlands. And I will also have a slide on this to give a bit more understanding of this. And we are also using data from the regional transport model as inputs, for instance, the transport networks, but also the inter-regional freight demand, because this is the global target or the aggregate target of all the commodity demand that is the commodity demand within the region, but also with the external regions. For the second module, which is from a logistical perspective also very interesting, is the scheduling module, because in this part we have the formation of the round tours. So effectively, this is where the tour formation takes place. The shipments demand that will have to be collected and distributed during the day, they need to be scheduled in truck tours. This is simulated in the scheduling model. And the simulation approach is a stepwise application of a series of discrete choice models. And since we apply a shipment-based approach, we can take into account the constraints, such as capacity of a vehicle or the types of commodities that are being transported in the vehicle, to take them into consideration in the probability that a particular shipment is combined with another shipment. And apart from the characteristics of the shipments, we are also using characteristics of the locations where the shipments are to be delivered into account. So we know that round tours, they are more easily formed within dense urban destinations, because here you don't want to drive in and out of the city too often, and also because there's more more densely populated number of firms, it's also more likely that you have more shipments at closer distance. So all of these probabilities, we've estimated discrete choice models. And for more details about the technical modeling about this, there is an article about this model that is published in Transportation Research Part E. Well, then the data requirements, and for running such a model, what type of data do you need? In the Harmony project, we also try to transfer this model to different study areas. So we have chosen for a methodology where we are trying to use as much as possible standard available data. So data from local transport models like networks and zones with socially connected data. The location of logistic nodes, distribution centers. Part of this we have collected using simple APIs and collecting it from OpenStreetMap data. And also global firm statistics, like the size of the firms, in order to be able to create a synthetic firm population. And an aggregate commodity demand. This is also available for many of the study areas. And depending on the availability of road freight data, there can also be a tailored calibration plan. In this case, we are using detailed freight trip diaries, but an alternative source could be from establishment surveys, and we are using truck counts from the transport model to calibrate also the network intensities. Well, in this research, we are using a new and innovative data collection that is being collected by National Statistics. It's a so-called XML data. This is an automated truck trip diary, so the transport carriers, they are obliged to fill in a survey about truck diaries. This was normally a very labor-intensive task, so they were not happy to do this. So now they can do this automatically from the transport management system. The nice and the good thing about this data collection is that we have information about the vehicles, but also the routes the vehicle drove, so which intermediate stops, and what were the loading and unloading locations, and also the load that the vehicle was carrying. So we know what type of goods were transported and the size of the shipment. Well, this gives a very good empirical basis for all our model estimations. Well, there is a big privacy concern, so we cannot use the data directly into the simulators. We can only work to it in a secured environment at Statistics Netherlands. Once we have estimated our logistic choice models, we take them out of this environment, the choice models only, and we use the parameters in our simulators. Well, this is the more technical part of my lecture or seminar on the modeling. So I gave some technical details about what types of choice models are in the model, and also the type of data that we are using for calibrating such a model. Next, I would like to share some experiences with some use cases. Well, first of all, this presentation is about the first use case is about the impact of a zero emission zone in the city of Rotterdam. To sketch the background of this use case, in Rotterdam, the municipality has decided to introduce a complete zero emission zone by 2025. So this is rather soon, and it's also rather ambitious because it's not a low emission zone, but it's fully zero emission zone. And this will create a big challenge for all the local entrepreneurs to anticipate to that. Big transport companies, they can organize this. They can buy an electric tractor for their trucks doing this city logistic distribution, for instance, of supermarkets. But there are also many small shops and small transport carriers that do not have this funding available. And for this, there also needs to be another solution. So the city of Rotterdam, they have laid out a roadmap for zero emission city logistics, in which they define alternative solutions for this. This is by installing urban consolidation center on the edge of the zero emission zone, from which the last mile into the zero emission zone can also be taken place by this dedicated service. Well, this is the geography of the area. You see the complete study area, and in the center there's the city of Rotterdam. And you can also see that the zero emission zone, it spans almost the complete city of Rotterdam, at least the part where the people live and work, not the port, of course. So it's quite a large zero emission zone. If we zoom in, we have plotted also possible locations or likely locations for urban consolidation centers. An important assumption in this whole scenario is that, first of all, the green area can only be entered by fully zero emission vehicles. The proportion of the vehicles entering the zone, it will be done by a zero emission vehicle coming from the original location, but also part of the shipments that are being distributed into the zero emission zone, they will be consolidated via this urban consolidation center. And then the delivery and collection within the zero emission zone from the urban consolidation center, it takes place with a dedicated zero emission vehicle. This can be a cargo bike, but it can also be a small electric truck. This is just, the illustration is just indicative. And for each of the different logistic segments, we used different assumptions about the probability or the share that will use the urban consolidation center, and also what is the most likely types of vehicle that will be used. So these are all differentiated by the different city logistic segments. So it's different for supermarket distribution compared to parcel deliveries. Well, to go to the results, this plot shows the reduction in CO2 emissions along the network. Well, it's quite clear that not all the reductions that take place within the zero emission zone. It was assumed that the distribution of within the zero emission zone of trucks coming out of the zero emission zone, it was done by hybrid vehicles. So outside of the zero emission zone, they still have CO2 emissions, but inside the zones, they switch to the electrical engines. And this is so, we see a very clear reduction in CO2 within the area. But if we scale up and look to the impacts at the scale of the city of Rotterdam, we see that it's the total CO2 reduction in the city center. This is about 8 or 9% of the emissions of the city as a whole. Of course, you have to realize that in Rotterdam, most of the freight transport, it's dominated by the long-haul freight transport coming from the seaport. So this was also an expected result. And also at the scale of the study area of South Holland, yeah, this is of course just a small step into the direction of decarbonizing freight transportation. And we also saw that the rerouting of shipments to the hubs sometimes also leads locally to an increase in emissions, because yeah, some trucks have to make a detour. Well, this is one of the indicators that we can look at within the zero emission zone. So the types of vehicles that are being used at the city of Rotterdam, they were worried if the city center would be flooded with cargo bikes, if the assumptions, if the scenario of the transitions would actually take place. So based on our simulations, we can say that, well, this is not likely to happen. The share of new zero emission, low electric vehicles and e-mopeds, it's only 10% of the vehicle kilometers. Still, most of the transportation that will take place within the zero emission zone is by the conventional tractor-trailer combinations. Also, some specific output is this plot that shows the change in emissions for parcel delivery. Here we also see quite, for this particular segment, quite an increase of emissions on the orbital ring road around Rotterdam, because for many of the distribution of the parcels that now have to be taken first to the urban consolidation centers, the parcel carriers, they have to drive around the city to come to the urban consolidation center that belongs to their company. So this also leads to some less efficient. So there are also less efficient parts in this solution. So this is something to take into consideration in further detailing the legislation and the regulation for implementing. So all the general conclusions, well, yeah, the impacts are not trivial. And there's a high reduction within the zero emission zone, but at the city scale, it's 10%. And of course, it's a good step towards an ambition to reduce CO2 emissions in the city center. But if you really want to decarbonize long-haul freight transport and meet the climate goals that they are now discussing in the COP26 meeting in Glasgow, yeah, then we need much more measures. And this brings me also to the second case study that we recently did with the model. So instead of focusing only on the zero emission zone, we now wanted to look at the research question of, okay, if we want to fully decarbonize road freight transportation, what are likely scenarios here, and how can we simulate the impacts of these scenarios? So there's a number of recent studies that give a very good overview of how road transportation can be decarbonized. A very important initiative is the Fit for 45 initiative by the European Commission. They have installed this framework to say by 2030, so 9 years from now, they want to reduce the carbon emissions to by 55% compared to the 1991 levels. This is quite an ambition. And this is also made specific in measures that needs to be taken for this, like installing a network of charging stations for hydrogen vehicles, or introduce large-scale road freight charging. On the slide, I've also included a number of other different studies. We've also extensively used the ITF study on decarbonizing transport in Europe for the urban freight modeling. And there's a number of other decarbonization studies. Well, from this, we identified a long list of measures and clustered them into 4 different categories. So there's measures that are aiming at demand reduction, like distance charging, or measures for clean energy. The zero emission zone is an example of this, but there's also electrification of trucks and vans, and also cleaner fuels. Energy efficiency, and there are also different measures for this. This is much about the fuel efficiency of the internal combustion engine. Also there, a lot of improvement can still be made. And also driving behavior is mentioned as an important way of reducing the emissions of the conventional vehicles. Such reductions can measure up to almost 20% of the CO2 emissions of a vehicle, if a driver adjusts his behavior and accelerates and decelerates in a more sustainable way. And then, of course, there are also measures aiming at logistic efficiency with new last mile solution or improved modular loading units and the optimizations of the tools. And what we did, we used the literature to find evidence or other expert opinions, I should say, because there's not much evidence yet, but to use expert opinions about the expected impacts of these different measures. And in a stepwise procedure, we have implemented them in the simulator. Well, there are a number of buttons in the simulator that we can adjust. So there's unit prices, for instance, where we can introduce the road user charge for heavy goods vehicles. There are emission factors. Here we can simulate the impacts of a different driving behavior or fuel efficiency gains. There are logistic choice parameters to simulate more efficient planning. We also used the transition scenarios, so using exogenous scenarios to simulate a transition from one vehicle type to the other, or to simulate a transition to consolidation hubs. And then finally, there's also the option to assume a different commodity demand, global demand. And this is coming from the external scenario. So we are using a interregional freight forecast. Also take into consideration the shift impacts, for instance, over heavy road from a road user charge, because it's likely that if a road user charge is being introduced, there will also be modal shift impacts. So part of the road freight transport, it will shift to barge or train transportation. And this will change the commodity. Well, then the outputs, the impacts that we got from the model. This figure shows first of all, the historic trend in CO2 emissions of road freight emissions in the province of South Holland, in the study area. And the most top line, it shows the expected growth in emissions in the reference scenario. And then in a stepwise procedure, we have implemented each of the measures subsequently, in addition, to see in the end what is the total reduction in CO2 emissions. And we also plotted the target of the Fit for 45 policy in 2030. And we can see that if all these measures are being implemented, we can actually reach this target. I have to emphasize this was quite an optimistic scenario. So we took the upper bandwidth of each of these measures and implemented it in simulation. So if all these measures are being implemented, and also the expectations in the domain about the impacts, then we can reach the climate goals. In practice, of course, it still needs to be seen if this is also achievable at this short time scale. But at least this gives an idea of, okay, we can get there. And one of the next steps that we want to do is to develop some alternative scenarios, maybe some more realistic assumptions, or less optimistic, I should say, or even more pessimistic scenarios about this. We don't anticipate to the climate change. Well, conclusions and outlooks. So the goals, they seem feasible, but we need rigorous measures. Also, what we try to show with the simulations is that the impacts, they are locally very diverse, and urban simulation models, they are needed to make a more reliable estimate of the impacts. Well, the impact assessment here is based on optimistic assumptions, and we will develop also some alternative scenarios in order to be able to present also a bandwidth of the expected impacts. And of course, we can also use this type of impact assessment to track the progress of the decarbonization goals, to see 1 or 2 years from now what is actually happening now with the uptake of electric vehicles, and to start from this base year and modify our scenario assumptions to update our observations for how far we are on track. A summary of this seminar lecture. I try to explain the simulation model, and I hope you are convinced also that urban freight, it's a complex system with many relevant developments and also different stakeholders that needs to be taken into account. The models for this domain, they are gradually evolving from basic like 4-step models towards more advanced multi-agent systems, such as MassGT. I think this is a very good thing, and it's very necessary, because if you really want to describe logistic decision-making, you need to have individual decision-making because of the large variety in stakeholders. In passenger mobility, the difference between one individual and the other is not so large. Okay, it's gender, it's income, but it's not so big. But in city logistics, the stakeholders are very diverse. There can be very large transportation companies, there can be a big manufacturing plant, or you can have a small shop. All these stakeholders, they are very diverse. And in order to capture their constraints, we really have to simulate this at the individual level. And also new types of sources of big data. They are very necessary and they are around much more. And they also enable this model development. So I foresee a lot of relevant research in our domain in the coming years. And with the scenario-based analysis, I've tried to illustrate how such type of models that can be used to make a better impact assessment of the zero emission zone or these decarbonization scenarios. Okay, here I've come to the end of my presentation, and there's time for questions and answers, and I hope to discuss these with you. And thank you for your kind attention.